Welcome to Summarize Science. Today, we're looking at a solar event from July 16, 2024, that's challenging a major theory about our sun. For decades, scientists have tried to understand a phenomenon called long-duration gamma-ray flares. These are events where the sun emits incredibly high-energy light, gamma rays, for hours after a solar flare has technically ended. The leading theory was that these gamma rays are created by particles accelerated in the shockwave of a massive explosion called a coronal mass ejection, or CME. But the 2024 event just didn't fit that story. As seen in this chart, the Fermi Space Telescope observed gamma-ray emission, shown in panel C, that lasted for over 7 hours. This was a powerful and long-lasting event, creating some of the highest energy light ever recorded from a flare. However, the associated CME that blasted off from the sun was surprisingly slow, traveling at only about 600 kilometers per second. This wasn't the powerful, fast-moving shockwave scientists expected to see. Even more telling, the number of energetic particles that actually reached spacecraft near Earth was incredibly low. If a powerful shockwave was the culprit, we should have seen a massive flood of these particles, but they were barely detectable. The radio signals that act as a tracker for the CME shockwave also died out very early, a full 5.5 hours before the gamma rays stopped. So, if the CME shock didn't do it, what did? The researchers found the answer by looking at the sun in extreme ultraviolet light. They discovered these giant, arch-like structures of hot plasma, which are essentially huge magnetic loops hovering over the site of the flare. Amazingly, these giant loops persisted for the entire 7-hour duration of the gamma-ray event. This led them to an alternative explanation that fits the evidence perfectly. The new theory is that after the initial flare, particles get injected into and trapped within these enormous magnetic loops. Inside this magnetic cage, the particles are continuously accelerated over many hours, like pinballs in a cosmic accelerator. Eventually, they leak out of the ends of the loops and slam into the sun's surface, producing the long-lasting gamma-ray glow. So let's recap the important points from this amazing discovery. The weak CME, the faint radio bursts, and the lack of energetic particles all show that the old shockwave theory doesn't work for this event. Instead, the direct observation of giant, persistent magnetic loops strongly suggests they are the real engines behind these gamma-ray marathons. This could be a game-changer because it provides a new mechanism for how our sun can accelerate particles to such incredible energies. It suggests that these loops might be common, but we just got lucky with a perfect side-on view this time. Understanding this process is crucial for better predicting space weather and the high-energy radiation our sun can produce. Thanks for joining us on Summarize Science.